Aniruddha is a senior data scientist with experience over 5 years across various industry experiences for AI ML journeys. He's an experienced builder in the MLOps domain across various multiple cloud solutions for AI synergies. Aniruddha is passionate AI researcher to transform the data into a machine learning end-to-end production journey. It eases the life of the business user. And today we're gonna be talking about Kubeflow with the feature store end-to-end, training and serving the model, building those Lego blocks. Oh yeah, Aniruddha stayed up late. He's all the way in India. So a big round of applause for him. There we go, Aniruddha. Welcome to the MLOps Community Podcast, Meetup, whatever you want to call it. Happy to have you here.
Thanks for the intro. It's quite an interesting intro. Thanks for that, Dimitri.
Interesting. I guess that's the way you can call it if you're like, man, this was cringeworthy. What the hell? So I'm going to give it up to you, man. And everyone that is joining us, of course, if you have any questions along the way, feel free to ask them. I'll try and stop Aniruddha at an opportune moment. If we need to get that question right away, I will. And yeah, as far as that, I'm going to hand it over to you, man. Let's get working, building these Lego blocks. Lego blocks.
Okay, guys. Thanks for joining this community meeting from MLOps. And today I'll be talking about building the blocks for productionizing ML projects with feature store in Kubeflow Orchestration, right? So let's just give you a brief intro about myself. As Dimitriev gave, I just came across with 5 years experience in MLOps and data scientist. And presently I'm working in Publicis Sapient as an ML engineer, as a senior data scientist. Okay, so today we are going to cover, right? We're going to see the technology and the concepts and the use case, how end-to-end we can build a particular framework for Kubeflow and with feature store. And what is feature store and why we request feature store in our day-to-day life in our ML journey, and how feature store works, and what are the application of batch and streaming data in Feast, and how to build the Kubeflow part in CATIV hyperparameter AutoML component, and building the DAG operator of productionizing in Kubeflow, and serving the endpoint for prediction results. So I'll go through all the concepts and the ideas and the tech side, how to set it up and how to build your own feature store. And I'll show the code and the demo at the end of the session. So the touch-based components, these are the components which I'll be talking about, and I'll be using those particular components for this particular session. I'll be using the Docker, I'll be using Kubeflow, I'll be using Kubernetes, I'll be using CATIV and Kafka and Prometheus and on. So I'll be talking about each of the components, how and where we can apply those things in our ML ops projects and end-to-end. Now, so there are two parts of this session. One is the feature store, another part is the Kubeflow. So we can talk first about the features. What is feature store? Why we need feature store, right? I will talk about the feature store first. Why we need a feature store? So as we can know, whenever a data scientist kickstart their project, there is a need of a particular problem to solve, a business problem to solve. So most of the data scientists in a team, let's say about two to three people, they come into the project and they spend a lot of time in building the data pipeline and doing some duplication effort. Let's say we have three people onboarded in a project, and three people have different skill levels of experience, where some might have a good domain knowledge, let's say retail domain, some might doesn't have too much of domain knowledge. So they invest a lot of time in investigating the data, on pre-processing the data during the training and all. And at that time there is not a consistency of training. Some might be training with some sort of feature scaling, and some might training in some sort of feature scaling. So there is not a consistency between all the data scientists in the team, with lack of domain knowledge and lack of experience of particular features, right? Now, what are the feature store helps in the data ML engineer also? There are a lot of challenges. Now, for an ML engineer or a data engineer, they might have to copy or maintain a lot of data of features for production, which is going to be very difficult for in production. Let's say we have a project for classification of a fraud detection, right? Now, a particular data who has been scaled in particular format for a data scientist, now it goes to the ML engineer, data engineer, so they save the data in production. Now the challenge comes, another data scientist comes up with different levels of experience. He also trained the data, and he also pre-processed the data, and it becomes a maintenance issue in the data engineer perspective, and it requires a lot of fragmented ideas to maintain those splits of data and all. So at this time, here comes a feature store to have a master data to store in a scalable format, and can be used as consistency in training and serving. Now, let's take a journey how the workflow work without feature store. Now, let's take a use case, right? Now, when a data scientist comes up, they first collect the data from any cloud sources or bucket, or in a CSV format or any sort of format of SQL format. Now, what they do the data analysis first. After that, they do some feature engineering on top of that, and after that, they train the model. Right now, after that, it goes to the data engineer perspective. Now they train the model. The trained model will be loaded, and it has been used for the model serving and for the predictions. Now, what is the next scenario comes up? Now, the same person of data scientist has been given the same data. Now he is doing some data collection, data analysis, feature engineering, the same process. Now, what is the effort? Now, the two data scientists is working on the same data. So there is a duplication of efforts, right? And we have been maintaining two different training data for in production, right? Which is not good, right? In real-time production, if we maintain two different training data or serving data of feature engineer data, which is very difficult to tell which data or feature engineer data is good or bad. So there is a duplication of efforts with no single of truth, right? Now let's see how the workflow work with feature store. Let's say we have a centralized repository of feature store, right? And we have, let me pause it. So we have a scenario. Let's say the first scenario is like, we will do some data collection, we'll do some data analysis, and we'll do some feature engineering. Now, once we do that feature engineering steps by, let's say we have 2-3 data scientists, they've been working as a collective way, as a managed collective way, and they publish the data in feature store. Now we have a centralized repository where we have our feature engineered data. Now, what are the use case it can be applied, right? Now we have, let's say, two scenarios. We have a regression model, we have a classification model, and there are 4 data scientists in our team. Now they can pull out the data from the feature store, and they can use the data which has been feature engineered and can be used for model training. Similarly, another data engineer or ML engineer can be used that same data for model serving and predictions, right? And this is the first use case for regression. Let's say if the same data has been used for classification, they can use this model training and the model serving and the model prediction. So what is the underlying logic here, or the underlying benefit or challenges it overcome, right? We are maintaining a centralized repository of feature store, which we have scaled and as a feature engineered process data, and we have published it into the feature store. Once that, and it can be used across all the projects, across all the data scientists in our team. Now, what is feature store, right? Now, all we know, right, talking about feature store. Now, what are the features? Now, we talk about features. Now, each data and column in our data real time, as a retail or health sector or any e-commerce sector, we have features, right? We train the features and we do some pre-processing where we do a lot of analytics behind that to save the data, to train the data and on. Now, let's imagine like where comes the features to comes. Now, it solves 5 different problems in our day-to-day ML journey, right? So features it will have we will be using a Feast open source library and a package from Tecton and Google, and we'll be talking about that, right? So Feast is helping the data attempts the productionizing of the ML things. Now it will maintain ingestion of data, both streaming and batch data simultaneously in production. So we can have our ingestion from batch data, and we can have our ingestion from streaming data, let's say Kafka or Kinesis or in EMR or from any other sources from live streaming. Now we can standardize the features. Now let's say we have a retail domain and we can standardize a single data repository by feature engineered, and we can maintain that. And we can reuse those features of semantic references for our, and we can share across to our peers and fellow members, to other data scientists. Do you know what? We have a central repository which already have a feature engineered data. You can use this data for your model building or your predictions or for other use cases. And we maintain a single consistency serving a training layer of data. And the point of time of correct features. Now, at the time of training, we can pull out those data anytime, anywhere within the project to train the model. And we can monitor the model and validify the tracking the matrices with Grafana or any other dashboard. Now, there are 5 components in Feature Store: the monitoring, the storage, the transformation, the serving, and the registry. Now, what are the 5 components? The serving is like, it will give a low latency serving, let's say Redis data structure on the backend. It will be running, we will store the data, and it will quickly give us the performance data for our prediction with a low latency, with less amount of time. So with respect to that, we can use the serving layer of Feature Stored for your prediction in our real-time application. And there is a transformation. The second block is transformation. So we have batch transformation, we have stream transformation, we have on-demand transformation. So on top of that, we have a batch transformation. Let's say we have 10 millions of records. We can transform those data. We can push it directly. And we have a streaming transformation. Let's say we have a Kafka streaming connector, and we can push it directly with the transformation logic, which we'll apply. And we have a monitor, right? We can monitor the metrics. So each matrices can give some matrices like latency, throughput, or staleness, or availability, or capacity of a particular feature store or a project, right, in production. So we can maintain the matrix. What is the overall health of that monitor of a feature store or the central repository? Is there any bug, or is it break? Is there any health factor decreasing or not in production? And what is the registry? And registry is the important thing, where we are maintaining a centralized feature registry as a definition of metadata about as a single source of truth, as we can say, like a single repository as a feature engineer data to be saved and served across all the training and serving purpose. And the fifth block is like a feature store, right? A feature store with the data warehouses like data lakes. So we can say like the data as a snapshot. So the snapshot of data which has been captured in our feature engineered, it's stored in S3 bucket, in Snowflake or Redshift, right? And we can use DynamoDB, Redis, and Cassandra. So there are a lot of work going on in adding a lot of feature engineered storage in AWS and in DynamoDB and on the community, and we will be working on that. Now, what is feature lifecycle with a Feast? So there are 2 lifecycle in our ML projects, right? So let's say we have a domain data, and we do some analytics, we do some data transformation on top of that. And once we do this entire journey of loading the data and doing some analytics after that, we do some transformation, we're plugging the Feast on top of that. Now that data has been pushed into our feature store on central repository. Once we do that, right, and the same central repository data has been used for model training and serving. So this process we tell as a pre-engineered features, right? So those features who has been engineeredly, which we have been transformed, and we are using it here. Now, what are another semi-pre-engineered features? So let's say we have a domain data, we have some analytics behind that, and we just plug in the data and push it. Now, any sort of transformation, let's say scaling or skew scaling or reducing or balancing the data or of a classification problem, we can do that in the next step. Now, once we do that in a real-time training or serving, that can be applied here. So there are 2 processes in here, semi-engineered and pre-engineered features. Now let's take a scenario. How it works. Now let's take a churn modeling, right? Now let's say churn modeling contains 3 different tables. It's customers, transaction, payments, and tech support, right? Now each transaction of a particular customer ID has been tracked across a particular date time and key customer ID, right? Now we can publish this entire data as a central repository to across all the three Lego blocks as a central repository to our feature store. Now, once we required a master data for across all, what we can do with respect to date time, the record of event. So when the event has occurred, right, with respect to that of event of occurrence and the particular ID, we can pull out all the data as from the central repository, and it will give us the particular data as a CSV format or the data frame format in our Python. Now, how we maintain is same data across training and prediction. You can just see a data here, table, right? We are maintaining a single source of truth, a similar sort of data, a customer ID, date time, gender, and all the data has been consistent in trading. And similarly, the same data has been consistent for prediction also. So we are maintaining a single repository, a central repository of data, both for training and prediction. Now, what is Feast not, right? Why we heard about why you use Feast, what is Feast, and what is Feature Store. Now, what is Feast not? Feast is not about a workflow or scheduler like Airflow or Kubeflow or Livy, right? It's not a data warehouse like Hive or Snowflake, right? And it's not a data discovery like Data Hub or Amadeus, right? It's not a pipeline building orchestrator like Kubeflow or Airflow. And it is not a feature engineering tool also like Features tool or Pandas or Spark. And it's not a model versioning product also. It's like a data version or control or something like that. And it doesn't do any model serving here. It's like a Shandon or Bento or TensorFlow serving. And it will not never replace the collaboration among the team of data scientists. It will ease the life of the data scientist to maintain a particular central repository. So how it will benefit the data scientist across all the MLOps journey in our production, right? So we can share the central repository as a single data across all the team with minimal effort of time, and it will reduce the effort of those particular data scientists, right? And we can have it two different feature engineering data which will decoupled, right? And it will be a single data. And we maintain a single source of truth or information about a features. Let's say retail data. Let's say a 10-year experience guy of a data scientist and a 3-year experience guy of a data scientist. Both have been working in retail domain. So the 10-year experience guy might have a domain knowledge on top of that, right? And what he does, right, he gave some inputs to the 3-year experience guys, right? And they build up a central repository after feature engineered from his domain experience and from the 3-year experience domain experience guys. And they have collaborated and they created a central repository of data for training and serving. And so they are maintaining a consistency of data for training and serving. And it supports all the frameworks of machine learning like PyTorch or TensorFlow and MXNet. And it can be used for real-time access of features like any of the connectors or any cloud vendors like Google Cloud or AWS or Azure. Now, how it will work, how Feature Store will work. So on a high level, how it will work, right? So we'll have a streaming data. We can have our files or data sources from S3 bucket or a GCS bucket, and we'll have our feature store, and which will be used as a Redis or Beam as a Spark Beam, and it will be triggering some Spark job in Databricks cluster or EMR in our AWS. Now, it will then be used for training the model and serving the model for production. So this central repository as a red block will be consistent. I mean, it will take care of all the central repository of the data. So how we set the projects? We have a project ID and we set the features. So these features are nothing but the columns. And we have entities, which is the unique entities. That means we can tell like what is the unique entities behind a particular table, and what are the features we are be using for a particular prediction or training for any ML projects. Now, how the operational flow of Feature Store works with Feast, right? So whenever a data scientist onboarded into a project, let's say we have a data of CSV file or any retail data. The data scientist will first, they will just register the data or sources for in a Feature Store core. And once we do that, right, it will be registered as an ingestion start for, it will kickstart an ingestion, right? Once it kickstarts ingestion, right, it will subscribe a particular feature, a column or row as a message broker. Now this will subscribe that into our feature registry in our feature core. Now this feature core will subscribe or saves this particular snapshot of data as a historical store in any buckets. So it snapshots of any data in a ParQ format or any other format, it takes it and it saves it into any bucket of Google Cloud or S3 or AWS and any other place. Once do that, it serves another functionality. It serves as a metadata. So we store the metadata. Those metadata can be retrieved by any time, anywhere in the project once we subscribe that. And another part of feature serving is like online retrievals. So this is first part is the offline retrieval, and the second part is online retrievals. So the online retrieval is a feature retrieval for quick time predictions for in our productions. Let's say we have deployed an application, we built an application, mobile application, and we need a quick time response for our users or customers. At that time, we can integrate those feature serving, and it can quickly give us the data in with minimal microseconds or low latency, right? With respect to that. So this is how the administrator, the stores, the sources works. So this can be subscribed with Feast SDK. So Feast SDK can be applied with a Python or SDK, and we can use it in our Jupyter notebook, and we can subscribe our data, and it can maintain the central repository across all the administrator blocks. Now, going forward, right now we talked about feature store, right? Now here in this demo, we'll be using feature store with Kubeflow and Kubernetes, right? And we'll be building the entire end-to-end pipeline. How to build that, right? How we have now our features. Now how we build our TensorFlow pipeline. So right now I'll be talking just a bit of a Kubeflow and Kubernetes. What is Kubeflow and Kubernetes? So why and what is Kubernetes? So Kubernetes is a open source automated deployment orchestrator, right? It can be used for deployment, it can be used for scaling of an application, and it can be used for management of containers application. So you can deploy your Node.js application, you can deploy your Flux application, Fast API, you can deploy your microservice, you can deploy your anything in Kubernetes, and we can Dockerize those things, and we can deploy these things, and we can scale those things. So there is auto scaling also in Kubernetes, which can auto scale with respect to the minimum traffic. And we have a storage orchestrator, right, which can store the data in a PVC, in a persistent volume. And we have a secret config manager, which can add as a layer of security to our application, and we can monitor the metrics via Grafana or Prometheus in our production. What is the metrics of a pod or a workloads in Kubernetes? And we can expose any application to the outer world with network load balancer, which can be accessible to any DNS by a domain to any other users, right? So the next block is what is Kubeflow, right? So Kubeflow is a dedicated ML workflow or on top of Kubernetes. It's a simple, portable, scalable project, which is a machine learning toolkit for all the data scientists to use that for productionizing the pipelines end to end for any use case or of ML or AI projects. So what are the components Kubeflow provides, right? What are the components we can use in Kubeflow? So we have AutoML as a hyperparameter tuning. We have a Kubeflow pipelines, which will build a automation pipeline, which can be used as a recurrent jobs for a day-to-day. Let's say we have every day we want to run the pipeline. We can run it, we can schedule it. We have a serving on top of a KF serving, and KF serving can be wrapped on TensorFlow serving also on Bento ML or Sheldon. And we have a distributed training. So distributed training with respect to multi-worker nodes and chef nodes, where a worker and chef will run parallelly. And we have a Jupyter notebook environment where we can use our own custom environment for all the data scientists. And we have a training operator. So the training operator is on top of your MXNet or TensorFlow or PyTorch and any other packages. And we have a multi-tenancy. Any users we can onboard into Kubeflow, and we can separate their namespace and their particular user account or particular notebook for their own dedicated projects. And we have a multi-cloud integration in all the clouds across AWS, GCP, or local in MiniKF and in our local. Now, going back to features to Kubeflow, right? What we are going to do in this use case. So we'll be getting some data, and this data is for a classification problem for a machine learning, and we'll be ingest the data from GCS Google Cloud Bucket and do some pre-processing as a feature engineered. Once you do some feature engineering, we'll save the artifacts, then we'll do some batch ingestion within feature store. And once you ingest the data, we'll build the Kubeflow pipeline. Once you build the pipeline, we train the model, we will save the model into GCS bucket, and we will serve the model with serving, and we'll monitor the matrices of that particular serving layer, and we will automate the process. And this is the end-to-end journey which will be integrating here. And this is the high-level architecture for how the Kubeflow with Feast architecture. Now, how the process it works. So we'll have a data. So this data will be ingested, and we will have a Spark job. So we have attached a data proc cluster on, I'm using GCS Google Cloud. So I'm using a data proc cluster. So whenever I took the data, right, I will restore it for a Spark job, and will ingest the Spark job, and it will run the trigger a Spark job on top of that, and it will retrieve a data of historical data for my training. So any data which we have been pushed into centralized repository, it can be accessible from a historical GCS, right? And so the snapshot of data is already there in GCS, but we are calling from Feast core, right? So we have a SDK to ingest all the features, and it's all running on Kubernetes. And once we train the data, we have a CATIV as a component of AutoML, which is a hyperparameter training framework, which will train the framework. And once with that, we deploy the model in Cave serving, right? And we have another layer is an online feature Redis structure, right? So these are a low latency data structure Redis, which will predict on top of your incoming data with a very minimal time, right? And we will use the Redis to serve our Cave serving endpoint, and the user can hit this particular endpoint, and we can monitor the metrics in Grafana and all. And each Spark job, we'll have a Kafka also. So that Kafka will run a particular Spark job where we can ingest the streaming data to our Spark in our feature core, and with respect to Kafka, and it will run a trigger a data proc Spark job. So let's go to the demo.
In the meantime, I see somebody's raising their hand. They got a question. If you got a question, throw it in the chat and we'll ask Aniruddha.
Okay. Okay. So I'll just give a brief, right? There are 4 parts, right? I will be talking about how to ingest the data, how to pre-process the data. So there is with feature store and with Feast. Once we do that, we will publish the data in feature store. So once we publish that, this is the first part. The next part is like we're building the pipeline in Kubeflow and serving the layer. And the third part is monitoring the metrics in Grafana. So I'll break it into 3 parts. So first I will be talking about, let's say I'm taking a data. So this data is about a taxi fare trip details of Newark, right? Now, what would happen, like we have a driver ID, we have a passenger count, and what is the fare amount, right? And we have some latitude and longitude with respect to all the driver IDs. So we have 2 tables as a data source. And this is the particular classification problem, whether a particular driver is fare amount is profit or not profit. So this is a classification problem for ML, right? So this first notebook is talking about what are the feature engineer we are going to do here for our use case, right? What we are going to do. Now, first, we're going to check, is there any missing values are there or not, right? Once we check, the next check is like, okay, is there any ambiguous data is there or not? Something on the features. So you can take your data also, whatever according to your domain, and you can do your feature engineer. So right now I took this data, that's why I'm doing this sort of feature engineer. Once I do that, I can change the date time. So I'm changing my columns into date time format, right? I'm changing some of the columns which is not in date time format. I'm changing into date time format. The very next I'm doing, so I'm creating some target columns to transform my data into classification by checking the fare details. So I'm giving some threshold in my target column, whether a particular fare amount of a particular driver is a profit or not profit. Once I do that, I'm adding some external features. Now I'm adding distance traveled between 2 trips. So I'm adding some latitude, longitude, distance on travel between 2 trips. I'm adding a new feature. So we can add our features also according to our domain expertise. Now it can be retail, it can be health, it can be any domain. We can add as many as features with respect to your use case in your day-to-day project. Once you do that, there's a bit of a normal distribution is the on top of how I will check the skewness. Now the skewness is like, is the data has been well distributed or not, right? Is the data has been skewed or not? I am checking what is the skewness on top of that, right? So once I do that, right, I felt like there is a lot of skewness as 3.58, right? I will do some log transformation on top of that, or I can do some power transformation of scikit-learn which will transform your data into some and reduce the skewness into data. So now I'm transforming my features. I'm filling the missing values here with some mean, and I'm checking the plots also. Once I've done that, right, I'll save the artifacts. Now I have transformed all the data for my training, and I've saved the data for my features here. Now I'm saving that as a CSV file here in my local in my Kubeflow notebook. And by the way, this is a Kubeflow environment which is up and running. And let me just give it. Well, sorry to I missed that part. So this is a particular Kubeflow environment, how it looks, right? And what are the components are there? There is a notebooks, there is a persistent volumes, and there's a AutoML, the CATIV, and there's a pipeline, there's a run. So I'll be talking about each of the components. Now I went to the notebook. So my notebook, Jupyter notebook is running. We can have our all VS Code. I think it's a bit slow. Yeah, so we can create our own notebooks, and we can create our request CPU and memory and GPU, and we can attach a PVC to create a notebook on top of that. So just to give you a brief on top of that. Now, once we do that, right, we coming back to here, I've transformed all my data. I have saved all my data. I've transformed my data, and I'm saving all the features into my notebook, right? And this is a persistent volume which I have been attached, right? Now, once I've done that, right, I'll be using those particular 2 CSV files for my next set of steps, right? I can check some more analytics. This is like, what is the geographic heat map of a particular driver in a Newark, right? And we can go a lot of analytics behind for this particular data set. But for the time being, I went just a bit of analytics, not too much on that, to showcase what we can do and what we cannot. So once we do that, right, I have transformed my data and I have saved my data here, and all the 2 CSV files local is there present here. What are the next set of steps? The next set of steps is like to use our high-level architecture. This is how it looks like, to use this and to ingest the data. Now all the data is been there, right? We have saved the data. Now we'll have our batch data. Now this batch data of and the entity or fair CSV and this 2 CSV files will push that as an ingestion job, which will run a Spark job in our data pro cluster. So this is our data pro cluster, which is running in our Google Cloud, right? So once we do that, right, it will trigger a Spark job on the backend and will start ingesting the data, right? So this data we can retrieve it as a training features for our model training in production. So once we do that, we deploy the model. Now there is another case, right? We can for our model prediction, for a real-time prediction, we can ingest some streaming data. Let's say Kafka or Kinesis or any other client real-time data. Now we are ingesting any log events or real-time data, right? And we are ingesting it again, and we are using those real-time data for our online features so that it can predict very quickly and in the prediction and the production side, right? And this also will trigger a Spark job as a on the backend in data per cluster. So you can use your own cloud according to your native cloud, and you can deploy those as I'm using in Google Cloud. So I'm using the components of all the Google Cloud and the Kubeflow. So this is how the high-level architecture works. So we can have our data from S3 bucket also, but right now I'm using the local in our persistent volume data. So these are the 2 CSV files. Now let's go to that. So there are a few of the Feast SDKs which we're going to install, right? We have to install those Feast SDKs, and we have to install a few Kafka clients or Kafka SDK and Dataproc SDK to run those entire code, right? And once you do that, right, what are the next sort of steps? The very next set of steps is like, I have to initialize all the environment variables in my local. So I have to initialize all the environment variables. What is the Feast core? What is that data pro cluster name? And what is the data pro cluster project of my Google Cloud project? And what is the Spark staging location? What is the Kafka address? Now, how I can do that? So I have connected to my cluster in my local of my Kubernetes cluster is running. So kubectl get pods. So pod is the smallest unit, which is a Lego block of your Kubernetes where you have deployed your all the components. So I've deployed my Feast and all Prometheus and Grafana. So all are running up and running, right? So what is the endpoint? SBC is the endpoint, or you can say as a service which expose your So these all the services which have been running up and running in my Kubernetes cluster, and some of they have cluster IP, some have load balancer as the IP, which I'm using it right now. Now, after that, what is the next set of steps? I get the environment variables from there. I have to initialize all the environment variables for my operation. And once I do that, let's create a dynamic staging bucket. Now, this bucket is a Google Cloud bucket, which I'll be using it for our feature store, right? To save my parquet format data as a snapshot to the cloud. So once I do that, I have to initialize the environment first. So once I initialize this environment, all the environment variables I'm initializing, right? I can check, okay, what are the environment variables are there in my local, right? And we're starting with feast as a name. So these are the environment variables which present right now. Once I do that, right, we have a client SDK. So this client will try to connect all the services which have been deployed on the backend in my Kubeflow cluster, in my Kubernetes, which is running up and running. So once I connected a client, so this is the client where I've connected with all the services of my feature store, and I'll be using that further. Now, first I'll load the data which I've transformed from the previous notebook. I have the 2 data frames which I have transformed. Once I do that, again, I have to do some datetime change, because once I load, the datetime got corrupted. So once you do that, right, I will check the date types and all. And for rechecking, okay, everything is well and good. There are some float and there is some datetime objects. Once I do that, right, the very next step of our feature store journey, right, it starts here. Now, I have a class. I've created a class. I've created an entity. I've created a trip tables. So this trip tables is for my first CSV, which I have loaded. So there are 2 CSV files. So I have one entity. So entity is the driver ID. So this driver ID is the entity, right? And the other are the tables. So driver ID entity is a unique ID, which will be as a record of event. So this is the event occurred in this particular time of event. And we can tell driver 610685 occurred at particular event. So this is the entity for all the 2 tables. Now first we have to register an entity. So this is the particular driver ID, and we give some registry entity. So this entity, we have already loaded it here on top. These are the particular Python SDK we have already loaded. Entity, value type, feature table, feature, and client. And we'll be using that here on the back. Now what we are going to do next? First, we are describing the entity. Then we are describing the trip tables. So these trip tables are the trip labels actually. So I'm giving some labels. I will show what is the labels amount. So each features in my column, I can give a label. Let's say latitude, longitude, right? Or latitude, longitude, will I use it in dev environment, or will I use it in as a production, I'm a test environment? So I can give some labels to my all the features, or you can say columns in my data. Similarly, for the next table, I'm creating a fair tables, right? Some labels. So once I created a labels 2 functions, right? The very next step is creating a particular features for a entity. Now, the incoming table of trip features, what are the CSV? I have 2 CSV, 2 data frame. So I will pass the trip features. I will check what is the data type of, is it in64 of the column name? Is it a float 64? Is it in32 or something like that? Once I check the data type, I will try to register a feature. I will try to declare a feature. So this feature can be declared as a column name. Let's give a column name, give a name. This can be a string. What is the value of data type of that particular column name? Once you do that, give that particular column name labels. So I'm giving the labels. So I have already declared the labels. So I'm attaching a labels for each column and each features. So each features, I'm just declaring the name, the string, that particular data type, and the labels of that particular declaration, which I've done it here. So each columns, each data types, I am declaring it here. Similarly, for the other table, other pandas table, I am declaring this. Once I do that, right, the very first thing, these are the column names are there in my first table, right? Now, once I do that, right, first I have to declare the entities. Now this entity, I am declaring my driver ID. The first step is to declare the entity, to register my entity. So I have registered my entity as a driver ID, which is the unique ID to recognize what is the unique customer driver name or something like that. Once I've done that, right, I am registering the feature tables. I'm registering the second table, the trip features. So this first table contains all the columns. Now this, just carefully see, this is a trip statistics. I gave a tag, trip statistics colon, pickup longitude is the column name. Trip statistics pickup latitude is the column name. So this column name and the tag of trip statistics as a feature entities, which has been stored for the first table. So I have stored my entity, I have stored my first table, the very next table, I will store my second table. So this is the column names which present in my second table. So I'll be storing this particular driver ID, and these are the column names of my feature store feast for the particular table. I will be storing it. So I have registered three things. One is a driver ID, my first table, and my second table. So these are the declaration which I have done, right? Once I have declared, I have to declare a schema. What is the schema structure? How the schema will be saved, right? What is the size, pattern of your data? Now, once I've done that, right, I have to declare where you want to store your data. So I am storing the snapshot in my Google Cloud bucket. Once I've done that, right, I'm saving some location. Let's say I'm creating a folder in my Google Cloud bucket, and it will store the data like driver statistics by this. Now, this is a feature table. Now, this feature table will talk about few things. It will talk about what are the feature table name. So the first table name is trip statistics. What are the entities? So this is the unique entity which will declare or to identify what is the entity. So this is driver ID. What is the trip entity? So trip entity is my table names, or you can say the features. So these are the features which I have declared on top, right? So once I declare that, I have a batch source. So this is the batch data. So I'm ingesting the batch data. So I have to declare what is the batch data. So my declaration is file source, right? So file source is where is your data? So I want to save my data into parquet format, right? So I'm saving the data into as a snapshot to Google Cloud bucket as a parquet format. And what are the partitioning? So I'm partitioning my data as a date, right? And the very next step is, this is for my first table. The very next step is for my second table. So I'm creating a fair statistics table, again the fair driver ID, and the format which I'm trying to save it as a schema declaration. So this step is declaring the table schema, how you want to save your data as a snapshot mechanism to save it into Google Cloud bucket. Once I've done that, right, I'm still not registered. The very next step is registering. So the first step, I have declared the features. The next step, I have declared the feature table. The very third step is to register the features or data frame which you have loaded. Now, the client, first, how it works. So now we have a client. So this client will apply, right? The first client will apply the particular driver entity, trip statistics, and fair statistics, right? Now this entity, driver entity as an object, we've already saved it on top, right? So this is the particular driver ID which entity which I've saved. And this is a trip entity for that second table, so the first table, and this is the entity for my second table. Now I'll be passing and saving those data for my next set of registering of feature store client, right? Now how I'll do that? First, I have to call that particular function, and I'm registering the particular table. Once I do that, I'm checking what are the schema structure. Now this is the schema structure for my first table. The first table is trip statistics, is pickup latitude, longitude, and what is the value type. And these are the labels which I have declared earlier, right? And what is the tags, production, or you want to use for model, or you want to use for any other things. Now these are the second columns for my tables. This is the third column. Similarly, like that, we have all the column names and what is the data has been stored. Right? So data as a snapshot has been stored in GS bucket. And what is the time has been stored, the time of event, right? It's been at what time we have created this event. Similarly, I have the spec as a schema for my second table, right? This is a table where we are storing the data. Now, we have done with the registration. Now we are done with the registration of our data, right? What is the next step, set of steps? Now we have to ingest the data. So let's say this is the data which is present. This is the two tables we have to ingest, right? Now already have ingested data. Now this client.ingestion will ingest your data. So this trip statistics is the object which you have already declared earlier, and this trip tables is the table name. Now what will happen? It will try to ingest the data, and once you ingest the data, it will declare a message. It successfully ingests the data as a feature table, as a batch source, which you have declared above, and it has been pushed on the as a snapshot to GCS bucket. Once you ingest the data, so we have ingested the data in a feature store as a central repository. What is the next step, set of steps? The very next set of steps is to check is your data has been published or not. Once I can check with get feature table. So I can publish the table name, give the table name, just check into a dictionary. So it will talk about, okay, this is a particular table which is present in your feature store. This is a second table which is present in your feature store. So I have two tables with two names. One is strip statistics, another is fair statistics. So I have two tables or you can say two data frame which have been stored in feature store in central repository. So what are the next set of steps? So there is a batch online ingestion. So this is the offline ingestion, right? What is the online ingestion? So this online ingestion is a which will run a Spark job, right? Now let's say I'm running this job, right? So if I run this job, so start offline to online ingestion. So from offline, so this is the offline mode which you have done. So from offline to online ingestion, and the backend, it will use a Redis to ingest the data. So it will trigger a Spark job on the backend. Now, is it refreshing? So at 25 seconds, at just now, it just run into Spark job, right? From my online to offline, from offline to online ingestion, and it will talk about the labels. What are the labels are there? So this is for trip statistics, this is for batch ingestion, and this is for fair statistics. So I have two tables. So I'm ingesting my two tables from my local for my features offline ingestion to online ingestion, right? Now this will be used for my production serving. Now I'm just breaking it here another step. Now these are the two parts. One is the offline and it's online ingestion. So there is another way of ingestion. The another way of ingestion is for streaming. So we will have a Kafka. So we already deployed a Kafka, right? We have a Kafka topic, and we can create a Kafka topic with our Kafka broker, and we can push the Kafka, we can push some data as a streaming Spark job, right? Now how it will work. Now, let's say this is the Kafka broker as an IP, which is running in my Kubernetes cluster, right? I've created two Kafka topic. Now this two Kafka topic will ingest my data. And how it will work, right? Let's say I am publishing, these are the two tables already present, two topic is already present. Now this is the schema for my first table. So these are all the column names and the data types for my first table, right? And once I declare the schema, so this is the schema, right? I have to declare the streaming source. Now the first source which we saw is batch source. The next source which I am showing Kafka source. So this Kafka source will run with respect to what is the event timestamp. So this is my pickup date time column name. What is the create column timestamp? So this is the time where the event has occurred. You have to give the bootstrapper broker code. What is the IP address of your Kafka and where it is running? And what is the topic which you have to subscribe your data, right? Where this particular schema. So this is the trip Kafka. And what is the format you want to save it? So I have an Avro format, right? This format which we are loading it here. So this format we have already published it from Avro, and that will push this particular data and save the data. And this is the particular schema. So this schema I am passing it here. So once I do that, right? Once I do that, it will run a streaming job. Now, once I run that, again, it will run a streaming job. So it will run a streaming job. Let me refresh it. It will run a third streaming job. Yes. So it will continuously run a streaming job because this is a real-time streaming job. So we can continuously see what is the status of the job. So status is in progress. So it will be running continuously because as it is a real-time streaming job. So what we can do, I have my table, right? Trip details. I can push, let's say I'm pushing 1000 column or rows of data. I don't want to push too much data. I've already done it, right? Let's say I want to push 100 rows of data. So it will try to publish 100 rows of data, and this function will call this particular Avro method to subscribe my data. So these are the column, this is the table, right? Each row has been publishing as a topic, and this is the format which you are saving the data here. Once I do that, and this Spark job as on a Kafka, it will be running continuously, right? And we have to stop it, or else it will be running continuously. As it is a Spark job on top of the Kafka, so it will run on top of that, right? Once you do that, right? Once you do that, let's say I want to save some data driver ID for my further step for my model training or for my model predictions or like that. Let's take a unique some driver ID. I'm taking some driver IDs, 100 driver IDs, right? And I'm taking the features. What are the features? These are the features for my first table, right? Now, how I can retrieve quickly? Let's see. Now, these are the driver ID. I want to quickly retrieve the data from my feature store. And client.get online features, you have to provide the features. So this is the table name, which is registered trip statistics in feature store. And what is the column name, right? All the features, I want all the features as from my feature store to be published here. So I'm providing that particular list, and I'm providing which driver ID. I need this particular driver ID to be published here. Now I'm publishing this get online features, client.get online features, right? And it will retrieve the data here. And we can see this is the data frame which has been loaded in a quick time, right? So if I run this, so if I run this, I can see a data table with respect to a low latency, with respect to any sort of thing. We don't have to import data. We don't have to import a CSV. Only thing you have to import, we have to call just client.get online features, which can retrieve your data. Now, what are the next set of steps? The next set of steps is like, again, to push the next table, right? The fair table. So this is a similar format of table, which I'm publishing it here. With the Kafka source, again, it will run a particular Spark job in the backend, right? And again, I can publish the data, I can retrieve the data. So till this is just ingestion and publishing the data after features to feature scaling and all, right? What are the next set of steps? The next set of steps, we have our training data, or we have our central repository. Now we have to train the data for our Kubeflow pipeline. We have to build the data. And to do that, we have to save some artifacts. Now, few artifacts, what we need, we just need two things. We need driver ID, which driver ID we need for our training data. What are the event timestamps? So we are saving the artifacts, and what are the column names you want. So these are the feature statistics, two column names and trip statistics from our feature table, which will be used as a merge in my training in our Kubeflow pipeline. So these two artifacts I'm stored in my GCS bucket, right? I stored it into my GCS bucket where it is stored right now. Right? So I'll be using these particular addresses to train my model. Only thing I just need driver ID and event timestamp, and which columns you want to publish. Let's see how the second part of this, how to build a Kubeflow pipeline.
And Aniruddha, while you're getting into that part, we've got a question that just came through here. Could you elaborate on what is the difference of a feature store from a database where one would store individual features? So I guess the question is, what's the difference between a feature store and a database where you just store features? Yes.
So the major challenge you see, like we have to query a SQL query, right? And in database, we store some pre-processed data and we store it into some SQL query. It takes a lot of time to, let's say, millions of transactional data, and we saved it into in SQL, right? And when in production, right, we need a real-time, quicker way to serve the model, right, for training or serving the model. So here comes the feature store, which will act as a central repository. Anyone across the team or any production, let's say 2-3 projects, which is running across the same data, and it can serve the model with a fraction of milliseconds, right? And with respect to any query, any environment, anything, any SQL query, we can directly just publish which table we need, right? And which are the table columns we need, and we can quickly get it, and it can predict on the serving layer. And another part is like the training layer. For the offline ingestion, offline retrieval of data. And this is the online retrieval. On the backend, it is using Redis data structure, which is low latency database data structure, which is very faster, and it can serve the data in a real-time production environment. Now, what is another thing? The another thing is like your offline ingestion, right? That offline ingestion, which we can use across the entire projects, across every data scientist can call from anywhere with respect to any SQL queries, right? SQL queries is a bit different, right? Now this is a bit different. It takes a snapshot. It ingests Kafka data also. We can ingest our batch streaming data also in here, and we can store the features into a central repository, and any data scientist across the projects can use it. which is not there in SQL. SQL is a bit different. It's a query-based language, and it's a center. And feature store is not a data warehouse. It's not a data lake, right? It's completely different with respect to that. I hope you got the answers on top of that.
Yeah, that sounded good to me. If anybody needs any more clarification, let us know. Until then, let's see the next part of this. I'm dying to see it, man. This is really cool.
Yep. Okay. So the very next step, right, I will talk about how to build a Kubeflow pipeline. So there are a few pipelines. Whenever we load a data, we pre-process the data, we hyperparameter the data, and we train the data and serve the data. So I have broke all the components into 4 parts: feature store, which will retrieve the data, which I published in the center repository, and my AutoML CATIV, my training, and my serving. So let's say the first step. So the very first step is, so we need 2-3 things to create a pipeline. First, you have to have a Docker file. So this Docker file contains all your Python files to run the environment. So, and you have to install your requirements file. Let's say you want to install TensorFlow, scikit-learn, or packages. You can give it here, and you need a service account to access the Datapro cluster as you're running it, right? So because to access the Datapro cluster, so I'll be using offline retrieval. So that's why I'll be giving particular credentials, so Google credentials, right? So once you do that, right, for the very first step, you have to declare again the same environment variables to access those data from center repository. So anyone in our project, if they get access to this particular repository, I mean this particular credentials in our cloud platform, they can use that and in our Kubeflow environment. And the very next step is like, where is the data saved? Now, if the data is saved in a GCS bucket and Google Cloud bucket, we can restructure that particular thing and we can give it in a data frame format. If it is an S3 bucket in AWS, we can save it and we can retrieve it. And if it is in Azure Blob Storage, in Cloud Container, we can retrieve it. So we have our URL format where the data has been stored. And this is a particular function talks about, is your Spark job completed or not, right? And how we create a pipeline. The very next step is like, we have to first create the inputs to a pipeline. So these are the inputs or the artifacts which I've saved in my Jupyter notebook. It will be used here. What I am giving, I'm giving my staging bucket. The staging bucket where my Spark job runs, it will take the snapshot from there. And what is the target column name? What is your prediction of a column name? And let's say I want to give fast statistics target as a column for predictions. And what is the ID? So this driver ID is the driver ID and the entity and the timestamp which I've saved in my previous notebook. And the data source is batch and the features. And these are the column names and from the tables which I want to retrieve. So this JSON, and this is the data where I want to save for my CATIV AutoML. So this is the data which I'll retrieve and come as a data frame. Now how it works, right? First, I will initialize all the environment variables. This will call this particular function, and it will initialize the environment here. Or the very next step is like, it will we will load the data as a GSUtil from as a JSON as an artifact. Now let me show this particular. So this particular data, I mean the feature tables, I've saved it into a GCS bucket as a JSON format, right? So this is a list I've saved into a GCS bucket, and this is a data frame which I'm using in my feature pipeline. Now these two things which I'm saving it here as a local in a MNT. Now what is MNT? I'll talk about it now while building the pipeline. Now I'm reading the particular file from a particular location. Let's say the data.id. Now this data.id is a driver.id which I've said, and I'm reading it here. Now I'm changing that to a date time. Once I do that, the very next step is to initialize my feature store feast SDK client. Now once I run that, right, the very next step is to retrieve your historical features. Now these historical features will run a Spark job in a Datapro cluster on the backend, and it will try to retrieve the data from that particular location. So what it requires all the features, all the columns and tables, what is required, the entities as a staging. What is the entity timestamp? So this is the timestamp from that which we have saved earlier from the notebook. We were passing it here. And what is the staging bucket? So the staging bucket is already we passed where it is stored. And once you do that, right, it will run the Spark job and it will wait till the Spark job complete. It will take, I think, if I have 10 million records, it will take, I think 1 hour or something, some sort of time for retrieval. It depends on the time. For me, I have 30K rows. So it takes about 10 minutes or 5 minutes of time to retrieve the data from Spark job. As I'm running 2 CPU machine on Data Pro cluster, so my Data Pro cluster is configuration bit less. So we can have more CPU and RAM to retrieve data more faster. Once I do that, the very next step is very common, right? We can save the data for training into X-Train, X-Test, Y-Train, Y-Test. We can save the artifacts in our PVC. Now, what is this MNT? We have attached a 1 gigahertz PVC. PVC, you can, I mean, you can say like as a file store where we are saving the artifacts while training the data. So this will save the data and it will retrieve the data in this particular Python file in this feature store. Once you do that, the very next step is like for model building or for my CATIV. Now for my CATIV, what I need required? I need a few things. The basic steps, you have to again have to build a Docker image. You have to put all the requirements, and you have to pass all the libraries. And the very important thing is the logs. So CATIV will work when you save the logs, it will retrieve the logs on top of that. So I'm initializing my logs from a logging. Now this block is building my TensorFlow block, and I'm giving some optimizer. It will run some neural networks, and it will give us my model. And I'm creating a custom callbacks. So this callback is a nothing but for TensorFlow callbacks, which saves all the logs for my training the pipeline. The very next step is I'm passing all the arguments. So in this arguments is a log path where my logs will be saved for my TensorFlow training, and my learning rate from my TensorFlow pipeline, TensorFlow neural layer, but the dropout optimizer and other layers. So you can add your use case and you can add your sklearn framework, PyTorch. You can add all the things on your own according to your requirement. Once you do that, where is my data? So the data which I have saved, which I've loaded from the earlier, right? From here in this step. So in this step, I have retrieved the data. Now I'll retrieve the data and I saved it into pandas data frame. Now I'll be using the data for my next set of steps. So what is the next set of steps? The very next set of steps is like, again, it will split the data. Again, it will build the model and it will run the model and it will save the logs. Now this component will be using for CATIV. So I'll talk about CATIV, how it will work. So we'll Dockerize this entire environment. So each iteration, it will try to save the logs and it will try to see which is the best parameters for my AutoML. So once I do that, the very next step is my train the best artifacts. Now these are the artifacts which I am creating for my model performance. And these are the artifacts which we are using for CATIV. Now I am retrieving the CATIV artifacts. Again, I'm training the CATIV artifacts as a final training, and I'm saving the artifacts, this model in GCS bucket. So this is the bucket. I'm already passing it from here. I want to save my data. I mean my model, TensorFlow model in GCS bucket, right? So I'm saving the TensorFlow model again here, right? I'm doing some check like what is the probability and all, some sort of metrics check. I'm saving the metrics check, and this metrics checks what we are saving, we can check it into a Kubeflow pipeline, how it looks actually. Then the very next step, I'm saving the TensorFlow logs, and the TensorFlow logs can be saved, and this is the format for actually for Kubeflow and how we save the logs, the ROC and all. And once we do that, we're dumping the as a ML metadata JSON, right? And once we do that, the very last step is upload the model weights which we have saved in local in our PVC to GCS bucket so that we can use the model for a prediction, right? So what is a few things we have done here, right? The very few things what we have done, we are taking the artifacts from the AutoML CATIV, what are the best parameters, we're grabbing those artifacts, we're loading the data for our training, and we're building the model, we're fitting the model, we are saving the model. Again, we are checking some metrics, right? And the very next step is saving all the artifacts, accuracy, F1 score or something like that. We're dumping the results. And the very next step is like, we are publishing the model weights toward GCS bucket so that it can be used for our prediction. Now, if I break it down here, the very last step is the serving. So I will just pause here. I will go to the pipeline now. Now, these are the requirements which requires to build a pipeline. So these are the basic Kubeflow pipelines requirements. So but the very next step is like I'll be using V1 beta experiment and algorithm spec and all. Now, what is this actually? The very first step is required is max trial count. The very first step is like max trial count is like I need 24 trials. That means 24 times it will run. So it will run actually which one? It will run this model file 24 times to see which one is the best model parameters, right? And what is the threshold is giving? I am giving 3 times it can fail max, and I want to run 3 jobs parallelly, right? What is the objective of this particular training? I want to maximize my accuracy to 95%, right? And what is the next step? How you want to optimize? I'm giving Bayesian optimization till the time your model model achieve a particular accuracy. Let's try to train it. And we are giving early stopping. What is early stopping? So V1 early stopping spec will stop the training if the model accuracy is not performing good, right? It's not increasing. And the very next step is like std out. So this std out will be using the logs. So we saving logs actually. So these logs, so these are the logs which you are saving here. Yep. So these are the logs which you are saving here. CATIV will try to grab those logs, right? And it will try to see those into a UI and it will try to see which is the best parameters or not. I'll show the UI how it works. Once you do that, now we have to define the parameters. So this is learning rate. So this learning rate, if you see here, we have our learning rates as an input, and we are defining the space. Let's select a value from 0.0.1 to 0.001.5. And what is the spec for optimizer? And this optimizer is a list of 3 items. And what is the categorical units? What is a layers? What are the initializer? So all the parameters which are declared here, I am giving a spec here as a parameter from CATIV, right? So this will be as a pass argument applied to my all the specs. Once I do that, the very next step is to declare a JSON template. So this JSON is here as an API version in your Kubernetes, which will run your trial and a Kubernetes job in Kubeflow, right? Now this template contains a Docker image. So this Docker image is nothing but the Docker which I've created here. The entry point of this is model.py file. This model.py file is this file, right? And all the parameters which I have declared earlier on the top, I'm passing it here as a spec. And these are the 2 parameters which is not dynamic, static, which I've declared here, data and target. Once I do that, so I declared my spec here. So this is my trial template of my Kubernetes, right? The very next step is like to fit all the trial templates into V1 trial template. Now this trial spec is my final trial spec for my Kubernetes, which will accumulate all the trial parameters and my trial spec, which I have declared as a JSON format. The very next step, the API is V1 beta 1 spec, experiment spec. So this will take all the counts, how many maximum trials, what is the maximum trial failed, parallel failed, the objective parameters, whatever we declared from above, all the objects has been stored here in the experiment spec. So there comes the particular pipeline, how to build a pipeline. So we have a native YML format. So I'll talk about a bit of a YML. This YML, if you go here, this is the raw template for a CATIV. So this template, we have to fill it, right? We have to fill it to run this job in CATIV in Kubeflow, right? Now, how we do that? So this is a convert results. I'll talk about this. Before that, I'll talk how it works. So we have a DSL operator, right, in Kubeflow. So this DSL operator will try to take some parameters. So these are the default parameters which I am passing in my Kubeflow pipeline. Now, if you see, these are the parameters, nothing but these parameters. So these all parameters for all the Python files, I'm passing it here for all the serving and all. So I'm creating a volume of a PVC of 1 gigahertz, right? The very next step, what I'm doing is my feature store retrieval. So the which feature store retrieval is nothing but these are the parameters which I'm passing it here again. So this DSL container is your containerist application of a Docker image, which I've Dockerized it. I am passing it here. So this is a Docker image. So this Docker image, I am passing it here. And this is a Python file, which I already have Dockerized it. And these are the artifacts or which I'm giving it from outside. And I'm giving some memory as a set resource memory. I'm giving some 4 gigahertz or 6 gigahertz or some limit to run this particular container, right? So that it can train or retrieve the data very faster. Once I do that, the very next step is for CATIV. The very next step is CATIV is you have to give your experiment name. What is the name of your experiment? You have to give your experiment namespace. So in Kubernetes, we have all has an individual namespace. Let's say my name is Aniruddha Choudhury. I have my namespace Aniruddha Choudhury. And for other, we can have our other namespace also. And we can then the very next step is to serialize. So this experiment spec is nothing but this experiment spec, what we have as a master spec, which we will serialize it here. Once I do that, I want to run it for 240 minutes. So I want to wait. So my CATIV will wait for 240 minutes to complete all the training to finish, right? And there is a method called dot after. So after this method, right, it will try to run this method. So it's like a DAG operator will run it. Again, I'm setting some operator of some CPU unlimiter on top of that, right? So the very next step I'm converting the results. So I got my CATIV. So I have my CATIV route. Now CATIV gave me some results. Now I have to convert my results from my CATIV for my next training. So this particular function will take those CATIV results and try to see which are the best parameters and it will print the results. So once you do that, right, the very last step is your evaluation step. So this evaluation step is nothing but this particular training file. So the best parameters will come from CATIV. We'll load those particular parameters and again we'll train the model and save the artifacts. So this components will run after the CATIV and we are giving after OP. So this is the particular object of CATIV object. Once you do that, right, the very last step is like we have trained the model, save the model, we have our CATIV template, KF servant template. So this KF servant template is in a JSON format. Now this template, I'm showing it here, how it looks. So this template contains a inference serving and this is my serving Python layer, right? And I am using case serving custom template. So there are two functions. You have to get two functions. One is a load, which will load the model, right? And I'm loading the model. I'm giving the path of a model and my model in Jesus bucket. I'm giving the environment variables. It is loading the model. Once you're loading the model, it will go to the predict function. Is the prediction greater than probability of 45? Then it will be profit of a driver. If not, it's a loss of driver. And we have to maintain two things from this YAML. We have to maintain this name Sheldon serving and we have to maintain this name to this serving also, right? Now, once we do that, right, once we declare the name, once we have the name and we have a Docker image, we have to Dockerize this entire serving layer. Now, once we Dockerize it, right, we have to deploy it. Now, I'm deploying it my default namespace. Now, we can do two ways. Either you can do from Pythonic way or you can do from if you have a Kubernetes cluster, you can do that. If anyone doesn't have a Kubernetes cluster, but just the Jupyter environment, they can do that right here like this template. They can use this template. What they can have to do, they just have to change the bucket name. So this bucket name already I'm passing it as an input from, yeah. So this is the bucket name already in bucket. I'm giving it from on the top. All the artifacts, what are the, I'm saving it, I'm giving from a GCS path. And this JSON will try to replace this particular load from the template substitute, right? Again, the last step is like resource op. So this resource op will try to run this particular entire template and try to deploy it in a Kubernetes and Kubeflow. Once you do that, it will run after the step. And the very next step is to compile. So this will generate a particular YAML file and it will look like this. So it will look like this, a Kubernetes Kubeflow compilation DAG operator. So once you do that, you have to upload this pipeline. So there is a KFP client. This KFP client will try to upload a pipeline. So this how our Kubeflow looks. Now see, here we have our pipelines. So the YAML which I have generated, so the YAML which I've generated, I've already uploaded that. So this YAML DAG looks like this. Just a second. Yep. So the YAML DAG like this. So we'll have PVC, we'll retrieve the data, we'll have CATIV, we'll convert the results, it will train the best model, it will serve the model, right? So this YAML DAG will look like this. So either we can do a manual way, we can create run, right? We can choose an experiment. So I have already one experiment running, so I'm using that. Or we can have our own create experiment. Now I was using like this. So what it will pre-populate all the artifacts what I am gave in my particular DAG operator Python file. It's showing populating those things. Only thing I need, I just have to click start. So to start a particular job and a particular run. So already I have a run in my local in this system. So I'll just show that. So with API, how we can do the first, we can create an experiment. We'll get a particular experiment ID, right? So this is a particular ID of an experiment, and this is the YAML file which we have generated from the top. Now we are uploading that as from the pipeline upload. Once you do that, this is the particular pipeline API request will send you. And these are the parameters which you are passing as a post request, right? Which you want to trigger the pipeline. Now you can run a pipeline. Now if I click here, already I'm running a pipeline. So already I run a pipeline before this call, and the pipeline looks like this. So all the pipeline is a green status, right? So I can see the logs. I can see what are the input parameters I gave, right? What are the feature step? This is a Docker image, right? And I can see the metadata, right? What are the artifacts? Where did I stored? And all the feature components. And this is my CATIV output, right? And how the CATIV looks. Now let's go to the CATIV. This is how the CATIV looks. This will try to train all the parameters which I have gave in the particular arguments, right? And it will try to achieve the maximum accuracy. So in this, you can ignore the accuracy, right? We can have early stop. We can see all the trials. So I have run it 24 times, 24 trials, which is running 3 times parallelly. And it will tell what is the status of this and what is the accuracy and validation accuracy and model performance on each run, on each trial template. So we'll have all the trial template, right? And how it looks at the last, it looks like this. It will try to achieve an accuracy of 58%, or I mean, we gave 95%, but in this we are achieving 58%. But according to your model, feature engineering, we can increase the performance. So once you do that, right? So once you do that, right, how the model looks like, once you do that, we can directly serve the model here on a one go. We can directly evaluate the model, and we can click the model, and we can retrieve the model anywhere. So once we build the particular pipeline, we can trigger the pipeline anywhere, anytime. And it will, with respect to any sort of efforts, and we can maintain an automated pipeline to retrieve the data, to train the pipeline, and to convert the result to, and to serve the model. So now we have seen all the things of training and serving. Now how to use the serving endpoint for our prediction. So the very last step of our prediction is like, now we have trained the model with Kubeflow. We've saved the model to our GCS bucket. Now we will predict the model to get the output, right? Now let's see how it works. Now we'll be using a Spark cluster to Spark job to retrieve the data via Redis endpoint data structures, and we're using the cave serving endpoint for prediction. So again, I have to initialize those environment variables. So just for a check to retrieve some online features. Now for a basic check, I was retrieving a historical data. So this historical features will retrieve the historical data. Just for restructuring purpose, I was just running this offline, but we can just directly retrieve the online features. So once I do that, right, let's say I have a JSON format this data. I took a one row. I just took a one row. We can take any rows. Let's say I took 10th to 11th row, and this is my data. I created a post request, right, which will hit this particular URL. So this is particular URL, and this URL we can get it from my Kubernetes cluster of my case endpoint. And we're creating the header, and we are requesting the post request, and this response is giving profit of a driver, right? So the response is hitting up my cave serving endpoint. So this is with the offline retrieval. And what is the online retrieval? So this is where the application is more faster, right? So we don't have to worry about too much. It will be in microsecond or milliseconds to to retrieve the data from online features. Only thing I need, which driver ID I want to check it out, and what are the features to retrieve the data. So only thing I can call it quickly, I can retrieve the data, I can rearrange the column name for my prediction, I can restructure it a bit. Once I do that, let's take any row from this data. Let's take a 9th row or 9 by 10. So this is my features, all the features. Now I'm passing this again. So this is talking about profitable driver, right? So how we retrieve that? And there is an option, kubectl, get inference service. So my service is running in, my Kf serving is running in my default namespace. So my Kf serving is running a default namespace. So we can describe it in from my Kubernetes. So its status is true. That's why I'm hitting this particular endpoint. I'm getting the prediction results, right? Now, once we get the prediction results from my offline and online trading, the very last step is to monitor the results, to monitor my metrics, right? The very last step to see how it helps to monitor. So we have Prometheus and Grafana, right? So this already I've deployed it and already running that by connecting to the cluster. So you can see the matrices for the last 1 hour. What is the health matrix? If you execute it right, it will try to see what is the status of that. Yes, this will be not understanding to a bigger deal, right? But we can see the matrices once we get the domain expertise, how to use this particular application or product to use with respect to feature store or and to say execute the particular query, and we can connect to our Grafana dashboard, and we can create a custom dashboard to check the monitor the health metrics for my feature store and to monitor the matrices on top of that. Now we have a lot of matrices for feature serving, feature request, gRPC or memory bytes, low latency memory bytes, to see the total concurrency and to see the model object bucket and count sum, to check the distribution of the health metrics. Now the very last step is like to see the particular prediction health metrics. So this is a particular dashboard which we already have in Knative, which will try to see what is the model metrics and how is the model is performing. If I hit it again, so it will try to see what is the traffic. We can monitor the metrics. So let's see. So you can see I have created 2-3 times. I've hit the endpoint. So I can monitor the metrics. What is the request volume? 4 times I've hit it. So if we have a large amount of customers hitting this endpoint, we can scale it into a canary rollout in Kubeflow. We can have an auto scaling environment also. We can have a security layer also. And we can see what is this traffic amount and what is the pressure is on the endpoint. It is giving a very quicker response in an application, in a production, or it's giving it's a bad response, or it's like there is some bad request is coming on top of that. So you can see the volume of all the matrices, and we can see all the Prometheus environment, how it is working. As I'm connected to a particular local pod of my Kubernetes, so it's handling all the requests and checking all the requests, and that's how we can manage all the features stored from fees to building the pipeline and serving the endpoint and hosting it into Google Cloud, and that's it. I mean, I'm open to questions now.
This was pretty incredible, man. We just went through so much, and you talked so fast. I am impressed. That was very well done. So
Yeah.
If anybody has any questions, let us know in the chat. Otherwise, I think that's it. We'll start wrapping it up. Really incredible stuff. And yeah, super impressive. This is definitely very in-depth, and I'm not sure I was expecting so much. But yeah, you proved to come through. You said you were going to do all that. I was a little bit skeptical when I was reading what we were going to go through today, and you were able to do it all. So I think, yeah, I think nobody has any questions. If they do later on, and if there's somebody that's watching this maybe in the future on YouTube, and they want to get in touch with you, I know you're on the MLOps community Slack channel, right?
Yep.
So
Yep.
yeah, we can.
They can reach out to me on LinkedIn also. They can reach out to me in Slack. Anytime, any help on MLOps, I can help it out.
Perfect. Yeah, this was really great, man. I really appreciate it.
Thanks.
And yeah, from there, you all have the GitHub repo to follow along and hopefully create some really cool stuff with. So yeah, please let us know if you do use this and you do manage to find value in it. Contact us or let us know in Slack what you did and maybe share some stories with us. So that's all we got for today. I think that is the full presentation. Thank you so much, Aniruddha. This was
Thank you,
awesome.
Dimitri,
And
for
everyone
hosting me.
in the chat is saying thank you very much. It was
Thanks,
really
guys.
impressive.
Thanks, guys. Thanks, guys. Take care.